NASA's $10 billion James Webb Space Telescope recently captured a dataset that has the scientific community quietly on edge. The telescope focused its sensors on a target 124 light-years from Earth. What it beamed back is difficult to explain through standard planetary geology alone. The data in this scan is forcing researchers to consider the presence of biological activity, making it one of the most consequential observations in the telescope's history. For decades, the hunt for extraterrestrial life has focused on finding a second Earth, a small, rocky planet with a temperate climate. But this target, designated K2-18b, falls into a different category, known as a Hycean world. It completes a tight 33-day orbit around a red dwarf star, insulated by a dense, hydrogen-rich atmosphere. Beneath that thick gas lies a massive liquid water ocean that wraps around the entire globe, with no exposed landmasses. If an organism doesn't require a rocky surface to survive, an endless ocean like this could support an entirely separate biological ecosystem. To figure out what's beneath those clouds, astronomers use a technique called transit spectroscopy. As the planet passes in front of its host star, the telescope captures the starlight filtering through the edges of the planet's atmosphere. This chart shows the resulting data. The collected light breaks into a spectrum line graph, where each peak acts like a chemical barcode revealing present gases. The initial readout highlighted massive concentrations of carbon dioxide and methane. Both of these are carbon-based and essential for life as we know it, but they are also routinely produced by non-living planetary geology, like volcanoes. The true weight of this scan lies in a microscopic anomaly buried deep inside that exact same dataset. Right alongside the carbon markers, the graph displays a separate signature for a molecule called Dimethyl Sulphide, or DMS. On Earth, there is an unbending rule for this specific molecule. It is exclusively produced by living organisms. Chemically, DMS is unstable. It breaks down fast when exposed to starlight, meaning it cannot linger in an atmosphere on its own. Because it degrades so rapidly, finding it at high levels on K2-18b means something is actively and continuously producing it to replenish the supply. Through a process of elimination, the presence of this single molecule makes it difficult to explain the atmospheric makeup without an active biological engine running beneath the waves. We see the measurable impact of microscopic life right here on Earth, where massive phytoplankton blooms alter the chemistry and color of our oceans. If the data holds, an alien equivalent to that phytoplankton could be churning out vast quantities of DMS across a global ocean, 124 light-years away. Right now, astronomers are actively reanalyzing the telescope data and scheduling follow-up observations to verify the chemical markers. The scientific method demands caution. Researchers must rule out all previously unknown, non-living photochemical reactions before they can officially declare a discovery. Regardless of the final confirmation, the detection of DMS has provided a concrete target that changes the nature of the conversation surrounding this world. This observation forces us to reconsider our assumptions about biology. Life may not require a perfect rocky surface. It might adapt to extreme aquatic environments. Because these waterlogged Hycean worlds are far more common in our galaxy than Earth-sized planets, there are millions of similar global oceans waiting to be examined. We are no longer limited to guessing at planetary conditions by measuring shadows. We can now directly profile the chemical makeup of alien skies. To follow the analysis of the K2-18b data and upcoming observations, hit the subscribe button. With this detection, we are no longer looking for places where life could exist. We are documenting the chemical evidence that it already does.